In this example, we are going to import this astronaut module model. We will set up the discretely modeled joints, referred to as point joints. See them here. And these are basically spring or bush elements that have been used to model fasteners, either a single spring meant to model a single lap joint, or springs in series for double lap joints. In this case, you can kind of see the backup fitting there for this double shear joint. And so the joints that we're going to focus on are summarized in this technical paper, which is on our website. And we are going to be focused on the gusset parachute, main parachute fitting, which is a large metallic fitting meant to react the parachute loads into the structure, as well as the gusset to lids fitting up here at the top. Again, this is a paper that's available on our website that summarizes the analysis that we performed on this composite crew module. Okay, so we provided this finite element model in the software installation, and the additional file that you will need to follow along with this example is the template database. And you can add this template database in. Should be this one here. And to add a template, you simply add a template and navigate to the template database. And then we will be able to use this when we open the software as kind of a fresh start. When we open the software, we'll see on the splash screen, we have this template available, which is the one that we just mapped. So I'm going to start with that. I'm going to call this project crew module. And then I'm going to navigate to the finite element model that is, again, provided in the software install. Should be in a path similar to this. And I'm going to point to this crew module.dat file. And you can see the fin counts here. One of the important things that we want to make sure we do is we import the 1B connectors along with all the shells and beams. See the models popped into view back here. There it is. Before leaving this form, I want to go ahead and make sure that I set up my design cases. So I'm going to roll over to the FEA results tab, turn off temperatures and pressures. We don't need to import those. I'm going to go to open my design loads. I can see the different design cases that have been included on pad abort, high altitude abort, max cabin pressure, translunar insertion, drogue chute pulls and main chute pulls. So these are important. They'll come up later. These are the parachute cases that I was discussing earlier. And I'm going to go ahead and select all of these, right click and select limit factor. And I'm going to set my limit factor equal to 0.714, which is basically 1 over 1.4, where 1.4 is the ultimate load factor for space launch applications for this application. So I'm assuming that the loads in the model have already been scaled to ultimate, and I'm factoring them down for any limit analysis, or in this case for things like fastener, shear, yielding, and tension yield analysis on the fasteners. So apply, okay. And on this form, I'll go ahead and select apply again, and then I'll close this form. Okay, so again, here's the crew module. I'm going to turn off the shadow. There we go. And if I go over to the Theme tab of the tree, expand here, I can see that all of my pbush properties have been recognized and pulled in. By hovering over them, you can see the stiffness assigned to the pbush. So in this case, we did a very high stiffness approach, kind of a infinite stiffness, if you will, on the spring elements. You could also do it like a Hooth stiffness formulation, which HyperX actually calculates the Hooth stiffnesses, and we can, in a lot of cases, we'll copy and paste those into the pbush cards after a couple of iterations. Another thing I failed to mention on import is that we did also have include files. So by selecting this INC button on the tree, the Theme tree switches to an include file organization, and these were the basically include files associated with the different parts of the structure. This is going to be useful for us because now we can use these to create structures. So I want to make this arrow shell go away. I can do that by either clicking in the tree and turning it off, or a feature I like to use quite often is the surface select. Select surface select, and then I can grab all of these pieces of the arrow shell, right click, hide those. All right, and then for now, I want to turn off all of my 1D elements. I'm going to go back to my Theme tree, turn the include part off. So now we're back here, and I can turn my 1D elements, my RVEs, and cbushes off. Okay. So what I want to do is create a structure for each one of those includes that I just saw for this part of the crew module. So I'm going to go back to the include part of the tree, and then I'm going to select my arrow shell is turned off, my heat shield is turned off. Okay, I don't want structures for those, but I do want structures for my lids ring. And then I'm going to hold shift and select all the way down to my backbone fittings. So I selected all of these. I'm going to right click on the model, or I could right click on the tree, either one. I'm going to say create structure. And I want to create structure per include files, but I also want it to go ahead and import all of the property definition from the Theme. So pcomps, pshells, go ahead and select those, turn those on, and then I want to have it use laminate overrides and metal overrides. We'll talk in a few minutes about what those mean. But this will tell the software to look in the property definition for all of the portions of the model that you're creating structures for. It will attempt to match the material IDs for all of the Mat 8 and Mat 1 materials that it sees associated with those properties. And since we started with a template, we already had those materials assigned in the database. So HyperX knows how to pair those materials with existing HyperX materials to go ahead and build up your laminate definitions and your plate materials and thicknesses. So it's going to gather all of the design property information from the Theme. So we will not have to assign any designs to the model. That will be done automatically based on the property cards in the finite element model. Okay. So now I can go to the structure tree, And I can see that indeed all of those pieces of the model are now HyperX structures. More so, if I look at the designs, I can see that my aluminum 7050 design has been created. And if I edit that design, I can see that I have kind of a generic 7050 design property with a 2/10 of an inch thick, but you can see that overrides have been used to do zone by zone, to assign zone by zone thicknesses. And mainly these aluminum 7050 materials, you can see here that I clicked it, it shows that the fittings here, the main parachute fittings, are the primary location where that 7050 is used, as well as the backup plates here. And then the overrides will actually assign the thickness. So that's what that checkbox was, use metal overrides. Same thing here with the laminates. So the laminate P-count definitions have been imported and assigned throughout the model. And we can see that for the imported P-count laminates that use the same materials, kind of, again, the same kind of paradigm where the overrides are used to assign, the actual ply counts to each one of those zones. So it kind of cuts down on the number of properties that you see after import. Okay, so that's getting the, I guess, gross acreage as well as some of the fitting definitions. That's pulled those dimensions into HyperX. But now we want to create the point joints, which will reference those properties. And so to do that, I'm going to go back to the Fin tab. And I'm going to, let me turn off my coordinate systems here so you don't see them. There we go, it went away. So I can use these buttons at the top to turn off different element types or coordinate systems, hide them from view. And what I want to do now is select the interface includes. So again, if you're not seeing the tree in this view, you can select this include option, make sure that is being that is active. Then our include files will be displayed. I can create structures from those. And notice that this looks a little different now. It sees pbush properties, and there's some options here for creating a joint per connector or creating a joint per property. We want to make sure we're creating a joint per connector, and then we're going to turn this option on again, which is create structures per include file. There we go. Select create. All right. And close that form, go back to the structure tree. Now we can see those three structures are also in the tree. Highlight those, I can see the joints there. If you're not seeing them as large as mine, we can go to this view port settings option on the view tab of the ribbon, viewport settings. And I'm going to make my joint size kind of max that out to the right. And that should make these much larger and easier to visualize. And then we can, let's turn my mesh off here. There we go. Makes it a little easier to look at it. Turn this guy off. And then we can color by joint. That makes it a little easier to see as well. All right. So if I expand these out, these structures in the tree here, we can see that we have what we call point joints 3-member and point joints 2-member. Two members here, two members there. So what does that mean? Okay, well, this basically is indicating the number of plate planes of elements or members of the lap joint. So a two member would be a single lap joint. So there are two plates here with one spring element to connect those two. So that would be a two member or a single lap joint. The three member here, we have the plates at the top associated with the main parachute fitting. We have the composite laminates in the middle, and then behind it we have this metallic backup fitting. So this is a double shear joint, or what we refer to as a three-member joint. And these are also, the modeling technique here is using the RBE spring RBE approach. Okay, so this joint in particular is modeled with, again, we have the metallic fitting, composite laminate, and then the backup fitting on the backside. And it uses this modeling technique for the fasteners, where there are multiple springs in series and RBEs connecting those springs. So the RBE3s are the green, connecting those springs into the either metal plates or composite laminate sheets. And so HyperX will treat this approach as a single fastener, and will pull the shear forces from each spring element, transform them into the sheet coordinates, determine a bearing force on each plate or each composite laminate, and then we'll use the peak spring tension force in the tension direction and do a tension shear interaction for each shear plane of the spring. We'll talk more about that when we see the analysis results. Okay. So back on my structure tab, I am going to now assign designs for my two member and three member joints. So I can create those on my structure tab. I can create on the design tab, I can create my fasten joint, single shear, double shear designs from here. We also have riveted joints, so we have the kind of rivet table allowables that you would use for riveting metal sheet together. So these are the different fasten joint specific design properties that we have. But since we started with the template, we have some of those already available in our library. And what I want to do is I want to pull those out and use them. So if I go to the library portion of the property tree, I'm going to right click on design property. I want to show my design properties. And I'm going to scroll all the way to the bottom of the list. Actually, I can filter. I just want to look at the ones for joints. There we go. There's 3 of them here. Go ahead and select all 3, and I'm going to select project, include. All right, so I selected joints to filter just to these. Grab all 3 of these, project, include. So that pulls them in. You can see now there's green markers next to them. And then I'm going to go to the property tree under design joints, fasten joints, and now you can see the 3 here available. All right. So what I want to do is now assign those, and I'm going to go ahead and select my 2 members, hold Control and select both. Select this one, hold Control, select the second one. They're both highlighted. They're highlighted on the model. Then I'm going to take my single shear HL10-12 joint design, and I'm going to either drag and drop it onto the model this way, or I can drag and drop it onto the tree. Finally, I can right click, and I can also assign to visible selection. So however you like to assign things. When I do that, notice that now in the tree, my 2 members no longer say unassigned, but the 3 member still does say unassigned. So that unassigned has gone away, which means that it has a design property assigned to it. And so I want to now assign my 3 member, so I can select it from the tree. I can right click on my double shear. I can assign a visible selection. Same process, just repeated for the 3 member tree. All right, so what are these designs here? Let me right click on the single shear. I'm going to select edit. And what we see here is the joint design property. And some of the key features here are, first and foremost, we're in an analysis mode. So we're only analyzing the joint as specified. For our materials, we are inheriting the plate materials and plate or composite material, whatever the spring is connected to. We're inheriting those designs that are connected to the springs through the RBE elements. And we're also inheriting the thicknesses. We have assigned a fastener, a HL10, which is a high lot fastener -12. So that indicates the diameter. I can take a quick peek at our fastener library by right-clicking in this field and selecting browse the fasteners, and I can look at the fastener library. And the HL10-12 is specifically this fastener. I can edit this and take a quick peek at this fastener spec, and I can see each dash number indicates a shank diameter for the fastener. And then these are the different inputs that are required to do the threaded fastener analysis that we perform, which is basically the NASA 5020 analysis process. Okay, so we're using a 3/8 fastener -12. Close that for and cancel. All right. So now we need to tell it how we want it to process loads. And for this, we can do a element-based loads processing approach. So I right-click on the loads, FEA loads, create element-based. That means for each connector, we're going to look at the tension shear moment in the connector. It's going to do a, it's going to rotate those forces, those shear forces into the plate, the material coordinates for the shot elements that it's connected to, and determine a bearing in that direction and a bearing bypass load. Okay, so I'm going to go ahead and assign that element based to those joints. So select them all in the tree, right click, assign the visible selection. Again, you can drag and drop out of the tree or drag from one tree to the other, whichever you like to do. And then we need to tell it what analysis that we want it to perform. So again, we started with a template. So in this library here, I already have an analysis property set up. So I'm going to go ahead and go get the library portion of the tree, select right click and select show, and then go to my fastener 5020 bearing bypass analysis property. And I'm going to include that in the project. And then here in the tree, under analysis joint, we can see that fastener 5020 analysis property is available. Let me right click on that. What does that mean? So right click on this, select edit. The analysis property comes up. It has two failure modes. The first failure mode is our fastener analysis. So right click and select edit. We can see the different fastener analysis methods. And then we can look at some of the inputs for deriving pretension, for applied torque, torque variation, some different additional factors, fitting factor, joint separation factor, shear criticality factor, wet pin factor. All of those are included. So again, this is our fastener analysis criteria. If I select a quick help, this additional help will bring you to our help system, which talks in more detail about the different fastener methods that we're running. We're also going to be performing, if I go back to the analysis property, we're going to be performing the bearing bypass analysis on the composite laminates. And this uses the bearing bypass failure envelope that's specified for the composite material that has all of the E over D and T over D type correction factors that are assigned to it. All right, so I'm going to assign this to these joints. I selected the two designs that I've assigned, and all of the joints that reference those designs are highlighted, and then I can again right click and assign a visible selection for the analysis property. All right, so the three things that we have to do for any entity in HyperX to get it ready for analysis is the design property, which we assigned, the load property, which was the element based, which we assigned, and then the analysis property, how we want it to write margins. And then it's ready to go. So I can select all of these, right click, select size, which is basically performing an analysis. There we go. Joint analysis completed successfully. And then we can start post-processing the results. So I can select the legend, and I can see margins of safety. I can view, just like my panels, I can see controlling criterion. I can see where we are, it's larger. There we go. I can see where we are tension shear critical for the fastener, where we're bearing bypass critical for the composite, and where we are bearing critical for the metal fittings or metal plates. All right. So let me isolate only the 3-member joints. Okay, so go back to my tree. I'm going to turn off my 2-member joints. Again, 3-member joints being the double shear joints with the backup plates and the metal fittings. I'm pretty much isolated to this main parachute fitting. I'm going to go back to plot my margins of safety. All right. And then there's a nice little option here. If I select this open probe label, so that's here. I can select this min-max option. It will show me where my maximum margin of safety is and what my minimum margin of safety is on the structure for the margins that I'm plotting. All right, so I can see my minimal margin of safety is this fastener here at the base of the fitting. It's about negative 5 or 6%. And you can take a look at this fastener. I can select it. Right click, select analysis results. And I can see that this fastener in particular is tension shear interaction driven. So that's the same margin that I saw in the call out. And if I sort by margin, I can see that let's see, fastener shear. Oh, if I right click on it, I can select analysis details. I can see all of the details associated with that margin of safety. There's the same margin that we saw, bolt type. And then I can see the allowables and forces associated with that margin. And so what I'm looking at here, the shear load in the spring for that critical case, and then the stress ratios or strength ratios here for shear and for tension. And we can see that the tension one is actually above 1, meaning that our tension load is exceeding our allowable. So even without shear, we are critical for tension. That is already going to be failing just for pure tension. So what that tells me is we're tension critical. Even though it's an interaction, we're tension critical for that fastener. So that's an easy fix in my mind. It tells me exactly what I need to do. So I'm going to go back to my double shear joints, and I'm going to right click on my joint design, select edit. This is my double shear joint design property. We have the 3 sheets being inherited, the thicknesses of those sheets being inherited. I've got some pre-tension assigned, torque is specified here. And so what I want to do is change this fastener from an HL10, which is a shear fastener. I want to change that to an HL12. So before I do that, I'm going to pull up this HL1016, which is what we're using. Select edit, hold that off to the side. I'm going to go down to my HL12s, HL12-16. That is you can see here, that is a tension head fastener, right? So since we're tension critical, this should help. Take a quick peek at this fastener spec, hold these up next to each other. What we can see here are the shear properties. Let's see, that's a -5. Yeah, okay, so this is how it should look. There we go. So this is aligned up here. The shear allowables for the 16 are the same, but the tension allowable for the HL12 is much higher. So this is because the head of the fastener is larger and the collar associated with the fastener is larger, giving us a better tension allowable. All right, so we're going to go ahead and select the HL12. All right, apply. And then that's pretty much it. I can right click and select size. Let's see if those tension shear margins go away. All right, cool. Looks like we're all positive on this fitting. If I look around the rest, I can very quickly, see my min max, use the probe. So there again, we're still critical in this area, but we're no longer driven by that tension load. I want to quickly deviate. I'm going to show a couple things. You don't need to follow along, but back on that analysis detail report, it's quite nice because you can very quickly determine your critical design case for that low margin of safety. That's case 922. And if I select my loads and deformations for case 922, 922 is my main parachute pull case, which is pulling directly on this fitting. And I can select my deformation, and select the form shape, look at, let's say, factor this out to 10, give us a nice, there we go. You can see kind of what's happening here. The main parachute fitting is being pulled very, very hard on this one side, and the fastener that we found to be critical was this fastener here. You can see kind of the heel toe effect going on, where not only is there tension load, but there's shear, and then the heel toe effect putting additional tension in this spring. So this is a nice way to verify and understand what the applied load is causing and how that's causing the tension in that spring. All right. Turn this back off. And let's go back to my analysis results, show my margins of safety. And so we've resolved the negative margins in the 3-member joints. So that's good. I'm going to go ahead and turn those off. And I'm going to go to my 2-member joints here. Select those and turn those on. All right, so these would be the gusset to lids fittings and then the gusset to main parachute fitting. We have quite a few negative margins. And again, I'm going to go to my probe to expose very quickly my min-max. And I can see the lowest margin here. Select it, right click and select analysis results. And this is not as clear to me of how to resolve this because we have a lot of negative margins, in fact. The tension shear analysis for the bolt is negative, which means we need to upsize the bolt. But we also have negative bearing margins for the metal plate, and then bearing bypass margins for the composite laminate that's fastened through. So we need to increase the bolt size, but we also need to increase the thickness of the plate, as well as we need to add plies to the composite. And so there's a lot going on, and how do you know what the best approach is? How do you know the best combination? And so what we have here in our design properties, we've provided this single shear sizing advanced. And so I'm going to right click on that design property in my tree, select edit, and that pulls up the joint design definition. And notice that the mode that it's in is not only sizing mode, which exposes the ability to make multiple selections in your sheet and fastener selections, but it's in advanced mode, which allows us to specify the order of operations and how we want the software to attempt to resolve these negative margins. And so I've given it multiple composite materials to look at. I've given it multiple fasteners to look at. We'll review that in a second. I am allowing the plate thickness to vary, and then I'm telling it what is the first thing that I want you to do to try to fix a negative margin. What's the second thing? What's the third thing? That's what this sequence is. So the order of operations that I've specified here, number one is try a new fastener, upsize the fastener. Then increase the plate thickness to try to fix the negative bearing margins on the plates. Then increase the laminate thickness to try to resolve the negative bearing bypass margins. If you don't get positive margins, start over, go back to number one, select a new fastener. And so because this is on selections, if I right click, I can select and order my fasteners. We can see the different fastener types that I'm letting it try. The HL10-12, then I tell it to go to HL12-12. You notice that I can be very explicit in how I want it to try what fasteners in what order. It's not just going in order of diameter. I'm telling it to try the -12 for the HL10, then the -12 for the HL12, then go back to HL10 and try -14, try -14 for HL12, and then I'm basically just throwing everything I have at it and just saying, you know what, if those titanium high locks don't work, try some Inconel fasteners, a -12, and a -14 as a -16. Okay. And then for my composite sheets, I can right click and same idea. I have a number of different laminate thicknesses that I'm letting it try. Notice that I'm pretty close to quasi-ISO. These are fabrics. I'm pretty close to quasi-ISO for all of these, which is ideal for the bearing bypass allowables. And then for my metal plate, I'm still inheriting the 7050, and I'm letting it range between these thicknesses here. All right. And so I'm going to assign this to these joints. So you can select those by, these are currently referencing this HL10-12 joint design. Select that, and then instead I'm going to right click on the single shear and I'm going to assign the visible selection. Again, I could have drug it from the tree over onto the model. It blinked to indicate that it's been assigned, and then I can right click and select size. Okay. Then can kind of get a top-down view here. Can kind of visually inspect and see, look, they look all positive. I can verify that by selecting min max. You can see that indeed I do have all positive, one that's pretty close to zero. That's good. A lot of them are fairly close to zero. I can see visually what fasteners were required. Sizing results. Fasteners. Where did it want? Inco fasteners. Where did it want? High lock fasteners. You can also see, plate thicknesses and required thicknesses and things like that for each joint. So that's how we perform sizing when we have multiple variables that we want to change to try to resolve a lot of negative margins, and how we can post-process and see where each fastener type has been selected. And that is the end of this demonstration. Stop the recording.